again, Gary Zacharias here. I want to look at another book. This is part of our podcast, the Apologist bookshelf. Hang on, put your seatbelts on and get ready. I want to take on another book by Hugh Ross. This one's called Improbable Planet. And the reason I say that about hang on is that Hugh Ross is an intellectual giant. He's really interesting. He is on the cutting edge of what's going on in the world of science when it comes to connecting with Christianity. And this book, I've done a podcast on it before. It's subtitled How Earth Became Humanity's Home. So it's kind of the background of how the Earth came about. And you'll see that over and over again, there had to be some special, unique features that only an intelligent, incredibly intelligent, powerful being could bring about for us to be here. So I'm going to take chapter 5. It's called Site Preparations. And he said the first 740 million years of our solar system's history, it was a hazardous place to be. They called it the Hadean period, referring to Hades. There were asteroids and comets smashing into the Earth, and if you take a look at the inner planets, Mercury, Venus, Earth, and Mars, you can see they'd just been peppered. And there were all sorts of violent solar flares and solar bursts of all sorts of X-ray and ultraviolet radiation, but it actually enhanced the possibility for future life. So I think that's interesting. What else was going on is you have these gas giants forming way out beyond the Earth, way out beyond Mars. And they're finding out now that if you have these big monster planets way out there, they protect the inner planets from taking too many destructive hits from these asteroids and comets. And they have actually migrated. They're kind of a fence to protect us, but they've influenced the mass of the Earth, the distance from the sun, some of the orbital features. And then you have to have an asteroid belt out beyond the Earth. If you don't have any, that's bad. If you have a huge one, it would just smash into the Earth all the time, some of the asteroids. So that has to be right. And then Ross spends some time in this chapter on a moon-forming event. So he says at this point, what you have is the Earth has way too much water and too thick an atmosphere to have advanced life. And it doesn't have enough various heavy metals and radioisotopes that would drive plate tectonics and give us a magnetic field. So now, he says, if you want this planet to become a dwelling for people and plants and animals, something's got to change dramatically. So what happened? He said researchers puzzling over it began to see a connection with another mystery. How did Earth end up with this big satellite of ours, the moon? He says if you compare it to the mass of the planet, the moon is 50 times larger than any other moon in the solar system. And our moon orbits a lot closer than any large satellite ever discovered. So a lot of people are scratching their heads. But they've been doing a lot of ongoing research and using dynamic models and trying to figure out where'd the moon come from and to have the kind of qualities that it has now. And it says current models. Okay, so what are they coming up with? A just right impactor. Some other body smashed the Earth with just the right timing, just the right angle, and just the right velocity for the moon to form. And he says astronomers call this impactor Theia, Theia. And so he shows what went on as far as using computers to figure out the angle and how the moon smashed into, or the objects smashed into the Earth and created the moon. So now what? What do you end up with? So he says this was an intricately layered sequence of coincidence. Well, we wouldn't call it coincidences, but he said a lot of scientists do, that happened to prepare Earth for life, advanced life. So he says, here's what the collision accomplished, right? So it's not just smash, bang, and there you go, you got a mess. No, you don't have a mess. It says the collision replaced that thick atmosphere. And what it did then left in place a thinner atmosphere with just the right chemical composition so it could trap heat. It would have a little bit of transparency so you could get photosynthesis. It ended up with the right air pressure so people could operate, with lungs and all. And number two, it changed the Earth's mass and density, so the Earth was able to retain, thanks to its gravity, a large quantity of water vapor for billions of years, but not too large. Number 3, it increased iron in the Earth's core. So that's what you need to have a strong, enduring magnetic field to shield the Earth later from deadly cosmic rays and solar X-rays, and to prevent the Earth's atmosphere from just sputtering away like it's done on Mars. What else happened thanks to this object smashing into the Earth and creating the moon? Well, the collision delivered iron and other critical elements to Earth's core and the mantle just right so that you could produce long-lasting continent-building plate tectonics that would be just right for life. What else? Well, that quantity of iron that came, thanks to the collision, was just right to support ocean-dwelling phytoplankton. And, of course, in turn, that helped support the entire food chain in the ocean and provided oxygen for advanced terrestrial life. What else did that collision do? The Earth's interior was salted with some long-lasting radioisotopes. Why is that useful? Well, you get a lot of heat from that, and that drove Earth's tectonic activity and volcanism, which is necessary. It recycles material up to the surface that can be used. What else did it do? So we're going on and on. Those are 6 points. We got 3 to go. Because of that collision, Earth's crust and upper mantle layers were peppered with just the right quantities of other chemicals, so that it wasn't enough to poison later life, but it sustained plants and animals and allowed eventually a global high technology civilization. What else? That collision produced a moon with just enough mass to stabilize our rotation and the tilt of the axis so to protect us from rapid and extreme climatic variations. What else? It slowed the Earth's rotation rate to a life-sustaining level. He says even the exact diameter and distance from the Earth was beneficial. So those are just some of the things that have happened. He says the Earth retained all sorts of volatiles as the accretion from the rest of the creation of the solar system happened. It said, let me skip ahead here. So you've got that going on. So that was chapter 5. I wanted to skip chapter 6. So that chapter 5 focuses especially on the creation of the moon and what that did for us. Chapter 7. Okay, now it says when life first emerged on Earth, it already had a complex ecosystem of unicellular species all over the place in high abundance. And so it says NASA scientists have been saying you need rock and you need liquid water, and that's how you get extraterrestrial life. That's all you need. And that's why they're looking all over the solar system now and all over the universe for this follow the water strategy. So you start hearing things like that. They're going to go to Europa, one of the moons of Jupiter, and because there's ice there, there's water there, and they're hoping to find life. And he has a quote here from Stephen Vogt, VOGT. His research team discovered an extrasolar planet way out there. He said, my own personal feeling is that the chances of life on this planet are 100%. Why? Because he said they must be common, these planets that have water on them. So that may be overly optimistic, but what's going on right now is astrobiologists are trying to find other Earths out there, twins, to see if they will have that liquid water and that solid rocks, and you put those together, and bingo, you get life. But he says, hold on. Researchers are going to, he says, we expect they will find planets that have water, but this is the crucial question. Just because you get water and rocks, does that automatically lead you to spontaneous generation of life from non-life? Well, no. And one reason is that you have to have a habitable zone for that planet. It's not just enough for what the planet has in it. It's where is that planet located. It's got to be a particular region around a star where life could be possible. And he said, now they're finding out it's not just one habitable zone, it's a lot of them. These things have to all happen if you're going to get life. He said it's a narrow region where all these habitable zones overlap. That's when you finally get the possibility of life. And he says, here's what's going on with some of the studies to date. 8 distinct habitable zones. Number 1, liquid water. Okay, so you've got to have your planet located someplace around a star where liquid water could exist on the surface. And then that, of course, means you got to have a certain kind of atmospheric pressure. So you got to have more than just a stable supply of liquid water. You got to have a habitat where you can have frozen water and liquid water and water vapor simultaneously over a long period of time. Well, they haven't found that yet. How about number 2? You have to have an ultraviolet habitable zone. Okay, so you want to have UV radiation that's not too strong or too weak. It's got to provide for life's needs. I mean, if you don't have it, several essential biochemical reactions and the synthesis of life-essential biochemical compounds can't happen. Okay, so that's not, if you have too little UV radiation. But what if you have too much? It destroys land-based life. So the quantity and the wavelength of UV radiation has to fall within a certain range for life to survive, and even narrower range for life to flourish. So here we are, we already have 2 habitable zones that have to happen, the water, the ultraviolet. How about number 3? You have to have a photosynthetic habitable zone. If you don't have photosynthesis capability, then large-bodied, warm-blooded animals would not be possible. So there's that. How about another habitable zone, the ozone habitable zone? Now, why do you want an ozone? Well, it forms a shield. It affects the amount of radiation that reaches the planetary surface. You want to have just the right radiation coming through. You also have, this is number 5, you have to have a rotation rate habitable zone. So how fast the planet rotates impacts the reflectivity of clouds and how much of the light will penetrate. So a rapidly rotating planet compared to a slowly rotating planet would have different kinds of clouds that wouldn't work for us. So it has to be just exactly the type of rotation. Here's something that sounds odd: obliquity habitable zone. What are they talking about? That's how much the planet is tilted. It says that determines the planet's surface temperature. So the higher the planet is tilted, the warmer the surface. So it warms the oceans and it cools the continents. So that has to be just exactly right. So let's try one more. The tidal habitable zone. So the planet, it's how far you are from a host star. The planet has to be near enough for life-essential radiation, but not get too close where you get tidal locking. Because due to gravity, of course, a star exerts a stronger pull on the near side of a planet than on the far side. So you got to be careful about how much tidal habitable pulling is going on. Here's another habitable zone that has to happen. Number 8, the astrosphere habitable zone. And what are they talking about there? Well, a star puts out wind. It's a release of radiation that pushes outward against the cosmic radiation all around it. And it says this wind creates a cocoon of charged particles surrounding the star. And a powerful stellar wind generates a plasma cocoon, but that's not good, right? A cocoon like that could blast nearby planets with all sorts of stellar particles to kill or limit the prospects of life. On the other hand, so here we go again, right? It's got to be just right. On the other hand, if you had a really weak stellar wind, you get a small plasma cocoon that's inadequate to shield the planet from blasts of deadly cosmic radiation. So just think about all those things that have to be exactly right. And it says these habitable zones change through time, both in their distance from the star and in their breadth. So he says the probability of life's origins by natural processes based on the things he's been talking about in this chapter may not be high at all. I said maybe as low as 0, and then he goes into more depth. So again, this book is really, really focused, and I don't know if it's for everybody, but I find this amazing when you realize the care and the crafted qualities that have to be here for us to exist, for any kind of life to exist. I always think about Paul Davies. Now, Hugh Ross hasn't talked about him here, but Paul Davies is not a Christian. He's an astrophysicist from Arizona State, not a believer. And he says we may be it in the entire universe as far as life, because it's so difficult to have life anywhere happen. So he's very pessimistic about it. He says this is it, probably right here on Earth, and nowhere else, not just in the solar system, but nowhere else in the universe have things been exactly right to provide life. It's so difficult to get life and to get it to stay. So I appreciate NASA. I appreciate the fact that they're searching and doing some amazing things on Mars. They have a little helicopter going, and these rovers have gotten big and amazing capability, and they'll have other voyages to planets. That's great. I love that. I think that's amazing. We get to see. It's kind of like we're there on Mars. But the astronomers are often saying they're doing it to try to find life. And we'll see if it helps their funding. More power to them. But we'll see. It doesn't sound very promising, but it shouldn't stop our exploration just to figure out what's going on and why. So I approve. I enjoy seeing what NASA's up to and other space agencies. But I think we're finding out that this Earth is special, that God made this for us and lavished care and attention on it. All right, well, that's interesting. At least I hope it's interesting for you. Thanks, and we'll do another podcast soon.